We often imagine the internet as something floating in the clouds, a wireless signals bouncing between satellites. In reality, our global digital life is anchored to the ocean floor. Over 99% of international data travels not through the air, but through physical cables deep beneath the sea. At the heart of this massive infrastructure is a single, hair-thin strand of glass. This strand acts as the primary backbone for the entire world's digital communication, guiding light pulses across continents and oceans at the speed of light. Light in a fiber optic cable is guided by a phenomenon called total internal reflection. This happens because of the specific materials used in the cable's construction. When a light pulse travels through the core and strikes the boundary with the cladding, it doesn't pass through. Instead, it reflects back inward, perfectly trapped within the core. This reflection occurs because of the refractive index difference between the two materials. As long as the light hits at the correct angle, it will continue to bounce for miles without losing its path. By bending this light path, we can guide information around obstacles and across continents, allowing data to travel at near the speed of light. Every piece of data, from a text message to a high-definition video, must first be translated into binary code, the universal language of computers consisting of ones and zeros. This electronic data enters an encoder, which translates these bits into rapid, precisely timed pulses of light. A pulse of light signifies a 1, while the absence of light represents a 0. These flashes travel through the fiber strand at nearly the speed of light, carrying information across the globe. Even in pure glass, light energy fades over long distances. This loss of signal strength is called attenuation. To restore the signal, we use erbium-doped fiber amplifiers, or EDFAs. These devices boost light pulses using pumped laser energy without ever converting them into electricity. By staying in the optical domain, we keep data moving at the speed of light across entire continents. Every fiber optic strand begins its life as a preform, a high-purity glass cylinder. It acts as the DNA for the final fiber, defining its optical characteristics. Inside a specialized furnace, we use chemical vapor deposition. Silicon and germanium vapors flow into a high-purity silica tube. As the burner travels, it heats the tube, forcing the chemicals to react and deposit ultra-thin layers of glass onto the inner wall. The process requires extreme precision. Even a single atom of impurity in this glass would absorb or scatter the light signals, destroying the data transmission. Once deposition is complete, the tube is collapsed into a solid glass rod, the preform. This rod contains the exact core-to-cladding ratio required for the final fiber. The drawing tower is the heart of fiber production. A high-purity glass preform is fed into a specialized furnace. Inside, temperatures reach 2,000 degrees Celsius, softening the glass to a viscous, flowing state. Gravity and mechanical pull draw the material downwards. As it exits the furnace, it narrows significantly from a thick rod to a hair-thin strand. Laser sensors monitor the diameter thousands of times per second. This ensures the fiber maintains a precision within a fraction of a micron. Once drawn, the fiber is cooled and a protective polymer coating is applied, completing the transition from raw glass to a high-speed data conduit. A single fiber optic strand is remarkably thin, roughly the diameter of a human hair. While made of pure silica glass, it is incredibly fragile on its own. To manage scale, individual fibers are grouped into organized ribbons. This structure allows engineers to handle hundreds of strands simultaneously without tangling. To survive the harsh environment, the fibers are bundled around a central strength member. We then apply layers of aramid fiber, like Kevlar, to provide the tensile strength needed for deployment. Finally, a waterproof buffer gel and a rugged outer sheath are applied. This transformation turns a delicate glass thread into a robust, installable cable capable of spanning oceans. Unlike terrestrial fiber, which rests in simple protective conduit, undersea cables are engineering marvels built to withstand extreme pressure and environmental hazards. Starting from the center, glass fiber strands carry the data. Surrounding them are copper conductors for powering repeaters, thick polyethylene insulation and layers of high-tensile steel armor wires. This armor shields the delicate glass core from the immense crushing pressure of the ocean floor and potential damage from anchors or marine life. Laying the foundation of the global internet requires specialized cable ships. These are massive engineering marvels, designed for one specific purpose: to transport and deploy thousands of miles of fiber optic cable across the ocean floor. Inside the belly of these ships are gargantuan circular tanks. Thousands of miles of armored fiber optic cable are coiled meticulously within these chambers to prevent tangling during the long transit. As the ship travels, a sophisticated linear engine precisely feeds the cable out through a stern chute. The speed is carefully controlled, ensuring the cable follows the contours of the seabed without excessive slack or tension, preserving the delicate glass fibers inside. A single fiber optic strand is like a highway. Without intervention, it acts as a single lane, carrying one signal at a time. Wavelength division multiplexing, or WDM, turns this single lane into many virtual lanes by assigning different colors of light to different data streams. The multiplexer combines these signals, allowing them to travel down the same fiber simultaneously without interference. At the destination, the demultiplexer separates the light back into its original component colors, restoring the independent data streams. The rise of generative AI has fundamentally shifted how we design the physical internet. Data centers are no longer just storage hubs. They are massive GPU-driven factories requiring unprecedented connectivity. Modern AI demands massive bandwidth and ultra-low latency. Because training large language models requires thousands of GPUs to synchronize in real time, the distance between data centers must be bridged by dedicated, high-speed fiber pathways. To achieve this, we are deploying new subsea cables optimized specifically for server-to-server synchronization. These AI fiber links utilize advanced multiplexing to treat continents as if they were in the same local network rack. To meet the massive demand of modern AI and data centers, we have moved beyond simply adding more colors of light. We have entered the era of space division multiplexing, or SDM. Previously, cables relied on just a few fiber pairs. SDM allows us to pack up to 32 fiber pairs into a single cable. This physical multiplication is the foundation for aggregate capacities exceeding 300 terabits per second. By creating parallel paths, we essentially create a multi-lane highway for data. Each fiber pair operates independently, allowing global networks to scale bandwidth at a pace that matches the growth of generative AI. It is a common misconception that satellite technology will replace fiber optic cables. In reality, over 99% of global international data travels through undersea fiber optic networks. While satellite systems provide a vital service for remote connectivity, they simply cannot match the massive, near-infinite bandwidth capacity of modern submarine fiber cables. Fiber acts as the global foundation for our digital world, while satellites serve as a vital complement for specialized, remote access. They do not compete, they complete each other. Subsea fiber optic networks are divided into two main segments: the dry plant and the wet plant. The dry plant consists of the terminal stations on land, where power feed equipment, or PFE, generates the constant high-voltage electricity needed to power the system. This power is delivered to the wet plant, which includes the fiber cables and the repeaters resting on the ocean floor. Every repeater needs electricity to amplify the optical data signal over long distances. Inside the subsea cable, you'll find a thick layer of copper conductors wrapped around the central fiber core. This metal layer acts as a high-voltage path, carrying DC current from the shore out to the repeaters. Because the ocean floor is conductive, the system completes a circuit by using the seawater itself as a return path. This robust design ensures a constant, reliable supply of power to keep the internet flowing across the globe. Fiber optic networks carry the lifeblood of global information. But as computing power grows, we need a new way to ensure our data remains secure. Enter quantum key distribution, or QKD. Standard encryption relies on complex math, QKD relies on the fundamental laws of physics. Because light particles, or photons, are used to carry the security key, any attempt to observe them changes their state. If an eavesdropper tries to intercept or tap the signal to read the key, the quantum state collapses. This physical disturbance alerts both the sender and receiver instantly. By integrating quantum mechanics into fiber networks, we create communication channels that are physically incapable of being secretly hacked. It is the gold standard for secure infrastructure. The digital backbone of our world is surprisingly ancient. Many modern fiber optic routes trace the paths originally surveyed for 19th century telegraph cables. We are not simply stringing cables in straight lines. The ocean floor is a complex terrain of canyons, trenches, and ridges. Cables must follow the path of least resistance. This makes the digital world physically tied to the Earth's geography. By choosing routes that avoid unstable zones or jagged trenches, we ensure the longevity and safety of the world's most critical infrastructure. The global network is held together by millions of kilometers of thin glass strands. These light pipes form the invisible backbone of our modern world. Within each strand, information travels at the speed of light. This infrastructure enables our economy, our communication, and our digital existence. The next time you look at a screen, remember the vast, silent, and incredibly fast world of light connecting us all. Thank you for exploring the technology of fiber optics.